Hey there, welcome to a video discussing section 4.7 on inverse trig functions. So this video is mainly for those who missed class on Friday, March 16th, and also happy St. Patrick's Day. Also, this could be for those who just want to watch this again and make sure they really understand what's going on with inverse trig functions. So before we get into inverse trig, let's actually talk about what is a function, what is an inverse, and then relate it to trigonometry. So remember, what is a function? For each input, just one output. Pretty easy, right? Remember, you have to pass the vertical line test to be a function. For example, off to the corner here, let's look at y equals sine x. If I were to graph that, hopefully you remember the graph of sine x looks like this. And if you draw vertical lines, you can see that they just cross once. So sine x is clearly a function. Now, what's an inverse? Hopefully you remember how to find inverses. We've talked about this in this class as well as last year in Algebra 2. What you want is you want to switch x and y and isolate y. Pretty simple, right? And now, in order for an inverse to be a function, you need to do the horizontal line test on the original equation. So let's take a look at y equals sine x. Now, if you were to switch x and y, of course you have this. And in order to get y by itself, you have to do something called the inverse sine function, which is going to be the main topic for this video lesson. And remember that notation, the -1 next to sine? The -1 kind of looks like an exponent, but it's really more of a superscript. That is the notation for inverse trig functions. But again, will this be a function? The problem is if I graph sine again over here, and if I draw horizontal lines, we can see that they're crossing more than once. In fact, they cross an infinite amount of times because sine is a repeating function. It's a periodic function, actually, more formal name. And so the horizontal lines touch that graph so many times. So the inverse of sine won't be a function unless we do something to restrict the domain, meaning to restrict what x values are being covered by sine. We're going to talk about that in a sec. So to answer this question, yes, sine does have an inverse, but not a function unless, and that's going to be next, if we restrict the domain. So restricting the domain means you're not graphing the whole thing. Like if I graph this right here and just that, my domain, hopefully you recognize the period, is from 0 to 2 pi. So that's 0, that's pi, that's 2 pi, and in the middle you have pi over 2, pi over 2, sorry about that, and 3 pi over 2. So again, if you draw horizontal lines, it's going to cross the graph more than once. What if I restrict it from negative pi over 2 to pi over 2? Now remember, if I keep going the other direction, negative pi over 2 is actually right there. It kind of looks like this. That is a sine graph. This is y equals sine x. I'm only graphing it in between those two x values. Now, the horizontal line test will pass if you restrict the domain. So this means that the inverse of sine x with this domain will now be a function. So the inverse called the inverse sine function is denoted by this. We talked about that. But now we can actually graph this and make sure the graph of the inverse is a function, meaning that the graph of the inverse passes the vertical line test. because the graph of the original passes the horizontal line test. Hopefully you got all that straight. So this is passing the horizontal line test. So now when I graph the inverse, obviously it's going to pass the vertical line test. Now, let's say the domain, again, is from negative pi over 2. Pi over 2, this is in interval notation. The range, of course, those are the y values, runs from negative 1 to 1. So we do the inverse, remember, switch x and y. So you're going from negative 1 to 1 and negative pi over 2 to pi over 2 for your range. Also, if I make a quick table for what I just graphed for sine x, but from negative pi over 2 to pi over 2, and look at the y values that go with them, obviously at x equals negative pi over 2, y is negative 1, x equals 0, y is 0, x equals pi over 2, y is 1. So now it switches for the inverse, right? Everything switches. X and y switch. So now negative 1, negative pi, 0, 0, and pi over 2, comma 1. So notice how my tick marks on the axes will also change. So you got that, that, and that. And the graph actually kind of has this really funky curvature, kind of like that. It's kind of a rotation about y equals x. If you took this graph here and rotate it about the line y equals x, it would look like what we have down below. So now y equals inverse sine of x is a function because we restricted domain on the original function, y equals sine x. And remember, we restricted from negative pi over 2 to pi over 2, which now becomes a range for the inverse graph because everything switches, right? X and y switch, domain is x, range is y. So whatever they were for the original, now they're reversed for the inverse. Some things to keep in mind before we start looking at this more numerically and finding exact values of inverse sine x. Keep in mind that that is not the same as inverse sine of x. Notice where the negative one is being placed than what I just circled. The negative one's on the outside. That's actually going to be this right there. Those are the same. When you put a negative on the outside, that means you do 1 over that. You know, we've seen that before as a negative exponent. Like we have x to the negative 1, for example. That's 1 over x. Not the case here. This is inverse notation. We see a negative 1 right next to the trig function itself. Remember when we had this for an inverse function, we had negative 1 next to f. So that's really what the negative 1 is being used for. It's more of a notation thing. And notational fluency is kind of a big deal in pre-calculus, especially when you move on to more advanced stuff like calculus and even past that. So we really want to make sure that we're very mindful of the notation here. So if you see negative 1 on the outside of parentheses, that's actually 1 over. If you see it next to it, that's more of just say, hey, I want the inverse sine function. Now, in case if you're not sure what inverse sine functions do, you remember we did have a test not that long ago. This is one with the ramp, and you're trying to see if it's safe to go up the ramp. And you have to solve for x degrees. Hopefully you recognize that sine x degrees is 2/5. So guess what? In order to solve for x, you got to do the inverse sine button in your graphing calculator, or a scientific calculator, or Desmos, whatever you have. So that's what inverse sine does. It helps us to solve an angle. So when you find the value of this, it's actually going to represent an angle. And it could be in radians or degrees, and what mode you set your calculator to. So that's really what we're after here. And notice how the y coordinates here, those are theta, right? So everything's reversed now. Before, the input was an angle, and the output was, the ratio of two sides of a right triangle, like opposite of hypotenuse. Now everything's all reversed. So find the exact value of inverse sine of root 2 over 2. Well, if we think about it, that's just going to be an angle. So that's all that's happening with that one. Okay. Okay, so find the exact value inverse sine of root 2 over 2. So what you could do is draw a triangle and work it out, or you can use your unit circle. Now, if you draw a triangle, hopefully you can see, I'll draw a triangle like right here. So that's going to equal theta. Remember, that's an angle, the inverse sine of root 2 over 2. So I put theta here, and remember, sine is opposite of hypotenuse. So basically it's like saying sine theta is root 2 over 2, where the root 2 is the opposite, and the 2 on the bottom is the hypotenuse. Now, if you do Pythagorean theorem correctly, you'll get the other leg being root 2. You recognize what kind of triangle that is. Hopefully you recognize it's a 45, 90 right triangle. So basically the angle is going to be 45 degrees, and theta equals inverse sine root 2 over 2. Remember, the inverse sine represents an angle. So the answer is just 45 degrees when you're asked to find the inverse sine of root 3 over 2. You could also use the unit circle. And actually, let me pull that up really quickly here so you can see for yourself. Probably easier if I just pull up an actual one here. Okay. So remember, sine on the unit circle is the y-coordinate. Where's the y-coordinate root 2 over 2? Obviously, it's right here. It also could be right here too, 135 degrees. But remember, we restricted our domain from pi over 2, which is 90 degrees, to negative pi over 2, which is actually going the clockwise direction, and actually it's coterminal 270. So if you think about the right half of the unit circle is pretty much what we're really interested in for inverse sine, because it covers all the y-coordinates on the unit circle, going from -1 all the way to +1. So 45 degrees would be the answer we would give, not 135. Even though sine 135 is root 2 over 2, we want to restrict the domain in order to keep inverse sine as a function, so it passes the vertical line test. So we just say the answer is just 45 degrees. So you basically can locate the y-coordinate on the unit circle, but staying within our range from negative pi over 2 to pi over 2. You could also use the unit circle. In this case, we're going to focus on the y-coordinate because we're dealing with inverse sine. If you're doing inverse cosine, you would use the x-coordinate, but today we're just doing inverse sine here. So using the unit circle again, now you could use a right triangle. Hopefully you recognize 30, 60, 90 ratios. They give this to you on the SAT, by the way. But you would see that hopefully 60 degrees would get us root 3 over 2. If you do sine of 60 degrees, that's x root 3 over 2x. You get root 3 over 2. So, yeah, the answer is just going to be that right there. Or look at the unit circle. Where is y root 3 over 2? Clearly, it's right here. Now, it's also right here as well, but we're not going to say 120. Remember, we restrict the domain from negative 90 to 90 degrees, or negative pi over 2 to pi over 2. So we're going to just say it's 60 degrees. How about negative 1/2? Now, where is y negative 1/2? Right here at 210 or 330. But again, we have to give our answer between negative pi over 2 to pi over 2. And if I'm going in the clockwise direction and I'm coterminal with 330, that's going to be negative 30 degrees. It's not any of these positive angles. It's definitely a negative angle. And it's negative 30 degrees. Sine of negative 30 degrees, we had this on our last test. Hopefully you recognize it to be negative 1/2. Because if you go to negative 30 and you locate the y-coordinate, that's the sine of negative 30 is negative 1/2. So the inverse sine of negative 1/2, remember we're doing the opposite. The input is the y-coordinate on the unit circle, or a ratio of two sides, like opposite or hypotenuse. And the output is an angle. So the output would be negative 30 degrees. Now, what you could do, when you get really good at this, is take the unit circle and just organize in a table like this. So notice we're going from negative pi over 2 to pi over 2 here. That's the restricted domain that we talked about for sine, so that the inverse sine could be a function. And of course, negative pi over 2 to pi over 2 for inverse sine would be the range. You remember, this is our output. This is our input. negative 90 degrees, negative 60 degrees, negative 45 degrees. I'm just converting the radians here to degrees because I know it's easier for some of you guys. And then if we work through these examples, you may want to pause the video and try this on your own. Okay, so if that's our input, you give the angle that goes with it, negative pi over 4, or negative 45 degrees. Or negative 1, give the angle that goes with it, which is negative pi over 2, or negative 90 degrees. Sine negative 90 gets you negative 1. Positive 1 is way up there. That gets you pi over 2 or 90 degrees. Then lastly, 0. Inverse sine of 0 would just be 0 degrees or 0 radians. So you can say 0 radians, or if you write 0 by itself, it's assumed as radians, or you put up the degree symbol if you want to give it as degrees. Okay, so that about covers it with this video. Definitely it's dumping rain right now. So stay dry, be safe, and I will see you guys